Let's continue in 6.6 and go through the calculus derivation of area mass density and center of mass of a lamina. So we have to picture this type of area here in orange as it has to have thickness obviously to be mass, but it's basically like constant and the same, so it doesn't change anything. It's like 1 or something. So think of it as a like a metal plate that's cut or something, and you want to find the center of mass of that. So this is the derivation for that. So we also call that when it's a constant density, we often call that a centroid, because it doesn't really have to do necessarily with actual mass, but really like where is most of the where's something condensed in one spot. If you were to take everything and it has the same thickness and density, where would it be for the center of mass? And so that's called a centroid. All right, so consider the lamina with area. So we were using area density, okay, of rho, and then now we're going to define the shape of it by the function values, right? By the function. So we're going to assume f of x is greater than g of x for all x in an interval. So something like this. Okay, generic sort of form. And then we can easily calculate the area. We've done that a number of times. So the area, because if you know area, then you multiply by rho and you get what? You get density. I'm sorry, you get mass. Rho is area mass density. So area is the sum of, and well now you're just going to add up these rectangles just like before. So it's the height is the difference of f and g, and the thickness in this case is your delta x. So the area is the sum of all those. So it'd be f of x minus g of x delta x. And if you integrate from a to b, you get actual area. So the mass of that is just going to be the sum from a to b of rho times that. So you just do rho times area and you get mass. So that's your calculation for mass, and rho is constant, so you can factor that out. You can have a changing density, and so rho can be a function of x, and it could change. And there could be some problems like that in the book. Don't worry about it too much, though. If it is, you just put it in there, and then you evaluate. If it's not, then you can factor rho out like a constant. Okay, so now let's look at the moment about the x and y axis. So we have that the distance from the x-axis to the midpoint is c. So the distance from the x-axis of the midpoint is what we want to figure out. So what we're going to basically look at is take these representative rectangles and find the center of mass of the representative rectangle. Excuse me. So find the center of mass, the representative rectangle, and then treat it like a point mass. And then we add them up. Just like we just treat them as point masses, just like we did above. So the center of the rectangle, so we can assume if it's constant density, we can assume that the center of the rectangle is the center of mass along the y-axis. And then your x value will be basically right in between. And we just choose, that's arbitrary because you're going to take a limit. So you can choose it to be the one right in the middle. And then that will be your center of mass of each rectangle. That's what we're after now. Okay, so what we look at then is you take this height, this f of x and g of x, you just add it up and divide by 2, and that gives you the y value. So we call that the average or midpoint. So average or midpoint is then a half f of x plus g of x. Okay, and that's the y value for the center of mass. So y value for center of mass of the rectangle. So if that's like saying y, right back up here, we basically took the y values here, that distance, and multiplied by mass. And we took the y value here and multiplied by mass. Well, that's what we're doing, y value here multiplied by mass. So that is the y value of the center of mass. You're just taking the midpoint of the rectangle itself. So the moment about the x-axis would be this. So moment about the x-axis will be that distance. So this is like your distance d. So the moment about the x is the distance d times, wait, wrong one. It's your distance d times your mass. So that looks like this. Moment about the x will be 1/2 times f of x plus g of x times your mass, which is rho f of x minus g of x delta x. So keep in mind that's the mass of the rectangle. And then this would be like the distance. So that's your distance from the y-axis. So it could go negative because you just add them up in that order and you're still going to get whatever distance that is. So it's like a position value, not a distance. Now let's do the moment about the y-axis. So moment about the y-axis is similar, but it's actually easier because the distance is just your x value. Wherever your x is, that is the center of delta x. So if you do this with Riemann sums and you pick your value in the kth interval, you pick it to be the midpoint of that interval, which is legal because that point is in Riemann sum is arbitrary. So you can be specific if you need it to be specific. All right, so that's going to be x. That's going to be x times rho, so times the mass. So distance or position times the mass, which is f of x minus g of x delta x. Okay, again, that's your mass, and that's your position or your distance. So let's look at the moment about x. The x-axis will be rho, if it's constant, from A to B, and then it's 1/2 f of x plus g of x f of x minus g of x dx. And then you can multiply that out if you want, and you get rho A to B, and you could do rho over 2 to make it even better. So 1/2 rho or rho over 2, let's do rho over 2. And then this becomes f of x squared minus g of x squared dx. So you can substitute, once you figure out, what's going on in your mass, you can go ahead and substitute into here for your moment about x. Moment about the y, you just put in the rest of the stuff again. It's rho A to B. Then it's x f of x minus g of x dx. Okay, then just as before, you have your x bar is moment about y over the mass. Y bar, moment about x over the mass. And then we call that a centroid. So the centroid or center of mass is x bar, y bar. So that's your derivation. It takes not too long to derive it. Yeah, I'm leaving off all the Riemann sum stuff this time. Not too important to see it every time. I just want to show you when it's pertinent to what we're doing. So this is I would never have you like memorize this one. This is usually something we'd always give you. Obviously, you'll be able to just look it up and do it. They do take a while to do these problems because you have 1, 2, 3 things to calculate, and they can take a while, even if they're just simple polynomials. So we'll go through one next. We'll go ahead and do another video because it would takes about, I think, more than that derivation time to do it. It's quite long. But we'll go through it once and then know the basic format and setup. Frankly, it gets more interesting in Calc 3 when you look in terms of actually 3 dimensions and you have a varying density, and it changes on the perspective of things. But the setup's the same, concept's the same, so we'll have to look at one. And this will wrap up the next video. We'll wrap up chapter 6.